Hello, here's Miss Walsh, and we are going to do day 4 question in the homework on optimization. So here we go. Good. So we've got the total surface area of a cylinder is 5,000. Find the dimensions that will maximize the volume and state this maximum volume. Okay, so what we're going to do is this is going to be our optimizing function, the volume, right? That's where we want to find the biggest or sometimes the smallest. And then the surface area is our constraint function, okay? Constraint, remember, that's what it has to meet, and it's actually our friend. It serves as information that we have been given. So let's start with that. So first of all, if you have a cylinder and you are given its surface area, just go to your formula booklet and let's just start with that formula. So what you have is you have 2 pi RH. Remember, that's the curved part of the cylinder, the body. And then what we're going to do is we're going to add the top and the bottom, okay? So this is this part of the formula, and then the body is this. Look at my color coding. Okay, and so we know that that must be 5,000, okay? It is stuck on that. All right, leave a little bit of space. And so now let's take a look at our optimizing function. Well, that is going to be the volume. Look in your formula booklet, you will see that that is pi r squared h, which is of course just the top times the body times the height. This is what you need to optimize, right? But of course, we're not happy. We're not happy because there's 2 variables. You've got your R variable, and then you've got your H variable, and that's a problem. We can't work with that. So what we do is we use our friend to isolate for one of the variables. Now, it's much, much easier to isolate for H. There's 2 R's. And so all we're going to do is just rewrite this with H being the subject of the formula. Okay, so subtract, don't divide. Subtract 2 pi r h from both sides. And now, and if you want, remember with these videos, you can pause it. Whoops, 2 pi r, okay? So what this is we now have our expression for h. How does this help? Well, if h is also equal to this thing, then what we can do is we can, instead of h, rewrite it with this thing, okay? Now, the reason that makes us ever so happy is because what we've just done is we've gotten rid of one of the variables, right? Everything is now in terms of r, okay? We can do a little bit of simplifying. You don't have to, but I just will. So the pi and the pi. Remember, you cannot cancel one on top, one on the bottom like this when it's a minus. But this whole thing is multiplied, this whole thing is divided, so we can. We can also cancel one of the r's. And so what we'll end up with is we will end up with r 5,000 minus 2 pi r squared. And if we wanted to expand, again, you don't have to. But if you wanted to, then you can expand. And this is your now simplified expression for the volume, okay? That's the hardest part, because now you can do whatever you want. What do they want now? You can optimize this. You can find the biggest one. Let's graph this. And so basically, just like what's happening is depending on what you set the radius to be, you're going to get different volumes, which is kind of interesting. Okay, so you can see this is a terrible window. The radius is not going to be very big, okay, because it's only 5,000 in total. So you might want to just, like, I don't know, make it maybe 0 to 30, and then remember, auto scale, and wow, well done, Ms. Walsh. And then you can auto scale it. Do remember that actually you don't need any of the negatives. And so now, extremum. And so now what you have, I'm just going to sketch it instead of taking the screenshot because you guys will be sketching it, right? So remember what's on the X here, that's our different radii, and then this our different volume, and then we get up with something like this. Do not draw into the negatives, that's it. And then you can see that your max is when the radius is this, and then the volume is this, okay? What did they ask? Find the dimensions. Okay, So just to be slightly more annoying, right? So then our radius, it is rounded, so I'm just going to use approximations. Our radius is this. Remember, the dimensions means that we do also have to find the height. How do we find the height? No problem. Remember that our height is, we have the isolated expression for it. Schwoops and schwoops. And so now just copy this, or 1628.6. So 1628.6, or you can use, so, and then I'm just going to calculate it. I like to just use unrounded values. You won't get thrown off like that, okay? So we had like times 16.28, and then divided by 2 times I times, and then again, oh, this should be squared. Yes, yes, Miss Walsh. Pay attention, Miss Walsh. Whoops. Squared times, go back down, 16.28, 32.6. So that's the height. If you were to check, if you sub it into the surface area with these dimensions, you should still get 5,000. Remember, we were constrained by that. And then if you substitute this, into here, your volume should be this, the biggest possible one, okay? So remember, set up your constraint, set up what you actually want to optimize, use the constraint to isolate for a variable, and then substitute it in, and then, woohoo, then party.